Hello everyone. Welcome to lecture 3 of this series on electrostatic conductors for JEE. I'm Dhiraj Madan and today we'll be continuing with that same topic. In the last couple of lectures, we have seen a few properties of electrostatic conductors, and we have seen one interesting problem also. And I gave you a couple of homework exercises based on the same. Hope you tried that as well. I'll shortly create a video on the solution for those homework exercises also. So today we are going to look at cavity inside conducting shells. That's the topic for today's lecture, and yeah, so that's going to be quite interesting as well. So let's see that. So let me give you a simple problem. Okay, actually it's simple provided you have studied this lecture, but let's see. Okay, so the problem is as follows, that consider a closed conducting shell. Okay, which has with a cavity and a total charge of Q. So the problem is to compute the charges introduced on the walls of the shell and the field inside the cavity. So it's as follows that, okay, let me draw it. So actually, the problem, along with the problem, there is also this specific diagram. So that the shell which we have is, spherical on the outside. Okay, and on the inside of it, it's some irregular shape. This is the medium. This is a cavity. This cavity is irregularly shaped inside, but on the outside, it's a perfect it's a perfect spherical surface on the outside. So this carries a net charge of Q. Okay, so this is the charge on that entire conducting medium. So you need to find the sort of total charges which are present on the walls inside and outside, and the field inside this cavity. Okay, so first of all, right. So basically, first of all, the idea is that the charge cannot lie inside the conducting medium, right? So let me recall the 5 properties which we have seen in the first lecture of this series. So what is the first property of conductor? So firstly, the electric field inside the conducting medium is 0. That's the first property. Secondly, there is no charge which is present in the interior of the conducting medium. Thirdly, any charge which resides must lie on the surface of the conductor. Fourthly, all points of the conductor are at equal potential. And finally, the electric field outside the surface must be perpendicular to the surface. So we have seen these 5 properties, right? So now you should always be, you should always remember these and be able to recollect them as needed. So now the charge in the conducting medium is going to be 0. The net charge is Q. Now, how much of it is present in inside on the inner surface and how much of it could be present in the outside surface? That is something we need to find. Okay. So now the thing is that let's try to solve this problem. So the first observation is that the charge Q can only lie on inner and outer surfaces, mainly that charge in conducting medium is zero. That's the first observation. Second observation is as follows, that okay, it's not an observation, it's something we have to reason out now. So if you look at that same cavity we had earlier, right? So this was the conducting medium, right? So this shaded portion is the bulk of the conducting medium. Now the thing is that now what I do is that I try to apply Gauss law by using a surface which passes through the conducting medium. Okay, so let me take this sort of a Gaussian surface, this dotted line, this dotted surface which passes within the conducting medium. So applying Gauss's law, okay, this is Gauss's law on a surface through conducting medium. What we have is that, so integral of E dot dA on the surface, right? So this must be 0, and this equals the charge enclosed on the inner surface over epsilon naught. This shows that the charge enclosed on the inner surface must be 0, right? So which means that the charge on the outer surface must be capital Q, because the net charge on inner plus outer surface must be 0. Okay. Now, okay, we know that the total charge on the inner surface now is 0, right? But the question is that, is it possible that zero charge can have some parts which are negatively charged and some parts which are positively charged on the inner surface, such that the net charge is 0? That's the question. So let me write down. So is it possible to have a distribution of positive and negative charges on the inner surface with a total charge of 0, right? That's the question. So let's draw it again. Basically that there can be some parts which are positively charged, some parts which are negatively charged. Is such a distribution possible that the net is 0? The answer is that no. Why? Because if there are going to be positive and negative charges on the surface, on the inner surface, then that means that there are going to be field lines, right? Because whenever there is a positive charge, it's going to be a source for field lines. Whenever there's a negative charge, it has to be a sink, right? And inside the conducting medium, right, so there cannot be a field line. So basically we could have had, the positive charge being the source of a field line with infinity as the sink. Similarly, negative charge could have been a source with negative charge could have been a sink with infinity as the source. But then in that case, those field lines which are coming and going out to the infinity, those would be going through this conducting medium. So that is impossible, right? So basically now the electric field line can start from a positive source and can end on the negative source within the cavity. So basically the answer is no. Okay, and so the idea is that a positive charge must be the source of a field line. Secondly, a negative charge must be a sink for a field line, right? Right. And infinity, right? Infinity can be potentially a source or a sink or both also, or actually none also. So all those possibilities are there for infinity. But right now in our case, right, so since there is a conducting medium, so basically the field line will be beginning from the positive charges and it will be ending on the negative charges, right? So if at all there has to be field line, it can go along this way. But here even so basically so we have field lines. So we have these field lines from positive to negative charges, right? But it's also impossible, right? Why? Because all points should have been at same potential, which is not true here. So basically, if you have a field line, then that means that there is a potential difference which is created, right? But we have seen property 4, which is that all points in the in the conductor they are at equal potential, and if there is a field line starting from one and ending at another point, then essentially that means that if you go along that field line, there is going to be a potential difference, right? So that potential difference we cannot have. So essentially the total charge is Q, therefore we have that. Okay, so basically there are no sort of induced charges on the inner surface. And as before, as we said earlier, the net charge capital Q must lie on the outer surface only. Right? So these are the charges induced. And inside the cavity, right? So you can apply a Gauss law and check that the net field is going to be 0. Okay. Yeah. So first of all, since let's draw that again. This was our conducting medium. So the charge on the inner surface is 0, and in fact it's 0 throughout this. Okay, it's not just that the total sum on the inner surface is 0 with some parts positive, negative. This total is 0 on the inner surface. And since the net charge is capital Q, so charge on the outside surface is now capital Q. Okay, so this is what the charges are. And now if we okay, so let's okay, so basically now if we want to compute the electric field inside this cavity, so we can check that essentially the idea is that there cannot be any field line that we have seen earlier, that there cannot be a field line which exists in the cavity. The reason being that a field line would indicate that there is a sort of a potential difference. So hence, essentially, there can be no field. So basically, we have computed the distribution of charges, and secondly, there is no field in the cavity, because if there is a field, there have to be field lines. Since the conducting medium cannot have any field, those field lines will have source and sink on the inner surface of the cavity, right? So if there is a field, the lines will have source or sink on the surface of cavity, implying that there is a potential difference, which actually is not there. Okay, so that's the main idea. Now, essentially what we have seen is that whatever charge was there has now just reached the outer surface. Within the in the inner cavity, there is not just no charge, but in fact there is no sort of electric field which exists, right? And okay, apart from this problem, even if you just take this sort of a cavity, okay, so whatever is the charge that will be there in the outer surface, whatever is some external charge also, some sources of external charges also, if at all they are there, then also we can actually construct that Gaussian surface. We can show that the net charge on the inner surface is going to be zero, right? And essentially there cannot be any distribution of these charges, because again, if there is a distribution, then there are going to be field lines. Field lines will indicate a potential difference. And whatever is the electric field inside, there is of course no field in the conducting medium. But of course, if there is no other charge in the cavity, then there is no field in the cavity also, because if there is some field in the cavity, that will have field lines which will exist, and they will have source and sink on the surface of this inner surface, and that will indicate a potential difference. So that is not possible. So essentially, the idea is that the inner cavity is shielded away from whatever is going on outside. So this is actually called as the shielding effect. We look at it in detail in the next lecture. But what you can see over here is that, if you want to, let's say, protect some instruments, let's say your electric gadgets, right, from external fields, what you can do is that you can place them in inside in a shell made of conducting material, and you can ensure that whatever is the field outside, there is no field going to be which will be there inside the cavity. And you can in fact do some sort of a simple experiment at home, that if you take your, let's say, phone, mobile phone, and you keep it inside, let's say some metallic utensils. Okay, so basically you can just take a pan and cover it with a plate or some lid. Okay, and that will create a cavity, and you place your phone inside. Then if you call to your phone, then it's not going to ring. Okay, so just check that, because that will there is going to be no electrostatic, there is no field which can penetrate through that cavity. That's the main idea. Now all this discussion was in the case when there is no charge which was placed inside the cavity. So once there is a charge which is placed inside the cavity, then this discussion will not be entirely true, because there can be a field which can emanate out from that positive or negative charge, and then the sink could be the remaining surface. So let's see one example for that. We have the following problem. So the problem is as follows, that okay, so in the previous one also, I'll give you a couple of homework exercises. So homework 1. So if the shells are concentric, right? So basically, if the surfaces are concentric spheres, to compute the electric field and potential of above configuration. The second part is that if the inner surface is not symmetrical, so what happens then? So these are the two questions which I'll leave you with. And basically, if it's not symmetrical, what is the field and potential inside and outside the inside and outside of this cavity? Right? So that's the question. Okay, okay, just think about this and let's solve another problem. So consider a charge small q. Okay. Inside the conducting shell with total charge capital Q. So find the charges induced on the inner and outer surfaces of conducting shell. So let's try to solve this. So there is a conducting shell. So the total charge on this is Q as before. But now what I'm going to do is that I'm also going to have it. Okay, so there, we have the same cavity as before. But now I'm going to place a small charge of I'm going to just place a charge of small q inside this cavity, right? So this conducting material, then there's this hollow cavity. And then there is this outer surface. This outer surface is spherical. And essentially the net charge on this conductor is capital Q. So there is going to be some charge on the inner and outer surfaces, which I need to compute. And that's the main problem. So how do we solve this? So the idea is that now, as before, if I construct a Gaussian surface which passes through the conducting medium, right? So, and essentially, then what I can see is that the net charge enclosed in the surface must be zero, right? Because the integral of E dot dA is zero. So, construct a Gaussian surface. Through the conducting medium. Now, if I compute integral of E dot dA over the surface, right? This has to be zero because there is no electric field inside the conducting medium. What would that mean? That means that Q plus Q on the inner surface, right? So I'm just going to label it Q inner. And on the outer surface, I have Q outer. That means that Q inner plus Q equals to zero. So basically Q inner must be minus of Q, right? Because the net charge enclosed includes this point charge of Q, and then there is a charge induced on the surface, which is Q inner. This Q inner must be minus of Q. Right? The net enclosed charge is the sum of this, which must be 0. Now, capital Q, which is the charge which is induced, uh, that must be equal to Q inner. Okay, I need to charge this for a minute. So that capital Q is now Q inner plus Q outer. Since small q inner, since Q inner is small q, so Q outer must be capital Q plus small q. Okay, so I'll just write it down here. This capital Q is going to be Q inner plus Q outer, which implies that Q outer is capital Q minus of Q inner, which means it is capital Q plus small q. Okay, so this is the net charge which is induced on the outer surface. Okay. And so basically now I'll leave you with a question. So the question is that in case of concentric shells, compute the potential and field of the system, right? Of the full system, both inside and outside the cavity. And second is that if inner surface is not symmetrical, or basically if it's not a concentric sphere, then compute electric field outside the outside basically the conducting shell, outside the shell. Okay, so these are the questions, these are the homework problems for today, and let's solve another interesting problem which is an extension of the sort of problems which we have looked at. So basically we saw that if you have a single sort of cavity, and essentially if there is no charge inside this cavity, and if the total charge on the conducting medium is capital Q, then there is no charge on the inner surface and all the charge resides on the outer surface, right? And also there is no charge inside the conducting shell. But what if there is a charge in small q inside the cavity? Then essentially there is a charge induced on the inner surface which is minus q, and the net charge induced on the outside surface is capital Q plus small q. So this is minus q, this is capital Q plus small q. The total is capital Q. Now what if we extend the logic to having multiple such shells? So let's try this out. Okay, by the way, these are not orbits of electrons or planets. Okay, this is just a sketch of the sort of shells. So let's say that we have a cavity. So let us say we have two concentric sort of shells. Okay. And there is a charge of small q1, point charge of small q1 inside the cavity of the innermost one. And the net charge on this conducting sort of shell, it's a thick shell, okay, is q2, and the net one, and this is q3. The question is to compute the sort of distribution on the surfaces. So how do we go about doing that? So well, what you can do is that you can apply Gauss law on a surface which passes through the conducting medium over here. So since the integral of E dot dA is going to be 0, and we know that Q1, point charge Q1 is enclosed inside this, so we know that the charge on the wall, inner wall of this sort of a shell is minus of Q1. Now the net charge on the second, on this first sort of shell is Q2, and minus Q1 is on the inner wall. So on the outer wall, we are going to have Q1 plus Q2. And now if I pass a spherical sort of a Gaussian surface through this sort of a shell, what do I get is that? So essentially now the net charge enclosed inside is Q inner for this one, and then Q2 from here and Q1 from here, right? So essentially this has to be minus Q1 minus Q2. And on the outer one, since the net is Q3, on the surface it's minus Q1 minus Q2. So overall this is going to be Q1 plus Q2 plus Q3. Okay, so basically if you can even extend this, let's say you have another sort of outer shell which has a total charge of Q4, then what happens? Okay, so in fact if you try that out, so you're going to get a few rules. So firstly, we see that in case of multiple shells, the charges on opposite surface are equal and opposite. And charge on innermost surface is negative of charge in cavity. Thirdly, charge on outer surfaces total charge on all conductors enclosed. So basically you could have applied the same logic over here. So Q1 is the charge inside. We applied Gauss law to compute that. Minus Q1 is the charge on the inner surface of the innermost shell. We could have also, we can check that this Q1 is, this charge is negative of the charge enclosed inside. The charge on this outer surface is now Q1 plus Q2. This is sum of the charges which are enclosed inside. So basically Q2 is the charge on this one and Q1 is the point charge. And similarly, on this inner surface, again, we have minus Q1 minus Q2, right? And finally, on the outermost surface, we have the net charge inside, which is Q1 plus Q2 plus Q3. So you can generalize this to more shells as well. And I would leave again with you with another homework exercise, which is to compute the electric field and potential for the above system. Assume concentric shells. So in the next lecture, we are going to look at the idea of electrostatic shielding. And till then, try out these homework exercises, and goodbye, and hope you enjoyed the lecture.